Hello everyone, welcome to episode 2 of Introduction to Circuit Design, and today we are going to be going over truth tables and K-maps. But before we get into that, real quick, I just want to briefly review some of the stuff we went over last time. So if you remember, last time we went over gates, and first up we have the NOT gate. If you remember, it just takes the input and inverts it. And then next we have the OR gate, which just needs any one of the two inputs to be on in order for the output to be on. And then we have the AND gate, which needs all of the inputs to be on for the output to be on. And then one new thing right here, whenever you see this kind of blue arc in a schematic or circuit schematic, it just means that these two wires are independent of one another. So you can see this is directly connected to this, and this one's directly connected to that. They have no correlation with each other. They are completely independent, which is what that blue arc is indicating. Okay, so now we have a circuit in front of us, and just like last time, we are going to do some Boolean algebra to see what the output of this circuit is. So we have two inputs here, A and B, and let's follow those two inputs to see where they go. If we follow A here, we can see it goes here over this arc and goes here into this AND gate. Okay, so one of the inputs to this AND gate is A. And let's see what the other input to this AND gate is. We follow this back around, follow here, goes to there. Okay, looks like the other input is B. So we can say that this AND gate's output right here is AB. Okay, now let's look at more of the circuit. So let's follow A again, following A. Okay, it looks like it goes to this NOT gate. So the output of this NOT gate we can say is A complement or A inverse or A bar, however you want to say it. And let's see where this goes. So A bar, or A inverse, goes to here. And it looks like this is an AND gate with something else. So A bar is being ANDed with something else. Let's see what it's being ANDed with. So we follow this guy back around, follow it back over here, and it looks like it's being ANDed with B. So this AND gate, let's see here, right here. This AND gate right here, its output is right here, is A bar, let's move it down, A bar B. Okay, and now we just have one final AND gate right here, which its output is right here, so let's follow the inputs for this AND gate. So one of the inputs is right here, let's follow it, goes down here, goes over here, goes up here. And looks like one of the inputs to that AND gate is A. So this input is A, now we need to see what the other input is, so let's follow this back. Okay, looks like if we follow it back, it is this NOT gate, which, what's the input to this NOT gate? B naught. So, or B goes into here, becomes B naught right here. And then B naught comes along here and goes into this AND gate. So we can say that this AND gate's input is A, B naught. And finally, if we look at all three of these AND gates outputs, they all go into this OR gate right here, and this OR gate's output goes into this final output right here. So our final output we can say is AB ORed with A naught B ORed with AB naught. So let's write that down. Y equals AB ORed with A naught B ORed with A, B, naught. Okay, so now we have the final output of our circuit, and right now you might be saying, oh my god, this circuit is so big, it's so complicated, this might just be a little bit too much for me. Well, what if I told you that this entire circuit is completely identical to this circuit? This circuit right here does all of what this circuit does, but using way less resources and way less space. So, how do we do this? Well, this is where our Boolean algebra is going to come in handy, and I'll show you why. Okay, so the first thing we're going to do is determine the size of our truth table using 2 to the power of n, where n is the number of inputs we have. So in our circuit, we have two inputs, which are A and B, so n is 2. And if we take 2 to the power of 2, it gives us 4. And this 4 is how many rows our truth table is going to have. So if we go to the next page, you can see our truth table has 1, 2, 3, 4 rows. And the two inputs right here, and one output y. Now you may be wondering where these zeros and ones came from. Well, basically what you do is for your rightmost input, so in this case B, you alternate zeros and ones every other slot. So you go 0, 1, 0, 1 for however many rows you have. If we had 50 rows, you'd keep going 0, 1, 0, 1, 0, 1, 0, 1 until you reach the bottom of however many rows you had. Then for the next row, you double the amount of times you use the same number. So here in A, we go 0, 0, 1, 1, and then if we kept going 0, 0, 1, 1, 0, 0, 1, 1, all the way to however many rows we had. And again, if we had a third input, we would double it again, so it would be every 4. So 0, 0, 0, 0, 1, 1, 1, 1, which we can see over here. So in this example, a 3-input truth table, n is 3, 2 to the power of 3 is 8, so that means we have 8 rows, 1, 2, 3, 4, 5, 6, 7, 8. And then your rightmost input, which in this case is C, alternate every other one, 0, 1, 0, 1, 0, 1. Then every 2, 0, 0, 1, 1, 0, 0, 1, 1. Then every 4. Then every 8. Then every 16. Then every 32. For however large your truth table is. Okay, so once you have the foundation for your truth table, you simply substitute in these values into your equation that you got for the output of the circuit, and then whatever answer you get, you put for the output of the circuit right here. So when A is 0 and B is 0, we just plug those into this equation right here. So 0 ANDed with 0 is 0, plus 0 or 1 ANDed with 0, which is still 0, and then 0 ANDed with 1, which is still 0. So 0 ORed with 0 ORed with 0, that's just going to be 0. Next, we got 0 for A and 1 for B. So 0 ANDed with 1 is still going to be 0. And then 1 ANDed with 1 is going to be 1. And 0 ANDed with 0 is going to be 0. So we have 0 ORed with 1 ORed with 0, which is 1. Okay, next I'm going to go a bit faster now. We have A equals 1, B equals 0. So this is going to be 0, this is going to be 0, and this is going to be 1. And finally, we have both of them being 1. So this is going to be 1. And because this is already 1 and it's just being ORed, we can just assume all of it is 1. So once you have your truth table, you can make what is called a K-map. And this right here is a 2x2 K-map. And other K-maps exist like 2x4 K-maps and 4x4 K-maps, but you don't need to worry about those right now because we're going to go over them in a later video. Just know that this right here is a 2x2 K-map, and you always use a 2x2 K-map when your circuit has 2 inputs. So this is always how your 2x2 K-map is going to start off. You're going to have A and B in the top left corner, separated by a diagonal line, and then 0, 1 on these two spaces, and then 0, 1 on these two spaces. So these correlate to their input. So right here, A is 0, A is 1, B is 0, B is 1. And then these blank spaces, which we haven't filled out yet, correlate to the output Y. So let's see how to fill in these blank spaces. So first, we look at the K-map and we say, okay, what is Y at A equals 0 and at B equals 0? Well, we look at our truth table and we see that at A equals 0 and B equals 0, Y is 0. So we'll just put a 0 right here. Next up, we have A equals 0 and B equals 1. So let's see what Y is when A is 0 and B is 1. A is 0, B is 1. Y is 1. So we put a 1. Same idea for the rest of them. A is 1, B is 0. Let's look at that. A is 1, B is 0. Okay, Y is 1. Put down a 1. And we already know that this right here is going to be 1 because, yeah, I think it should be obvious. So right here is 1. So once you have your K-map with all of the correct outputs in it, you want to circle the largest group of ones you can without circling a zero, and ones can overlap as well. So you'll see what I mean in a second here. So right here, you can see we have these two ones right here. So we can circle these two. So that'll be our first circle. And we have these two ones right here. So that'll be our second circle. If there was a 1 right here, then we would just circle the entire thing because that would be the largest group of ones. But of course it's a 0 right here, so we cannot circle the entire thing. Therefore, we only have a circle right here and a circle right here. Now, once you have your circles, you're going to look at where the circles are and then say which of the inputs is not changing over the course of that circle. So, if we look at this circle right here, we say that A is changing over the course of the circle. So, A goes from 0 to 1 over the course of this circle. If we look at B, B isn't changing at all. B is just always 1. So, we're going to write down B as one of our outputs. So, Y equals B. Okay, then we still have that other circle to worry about. So in this circle right here, B is changing. B is going from 0 to 1. So we're not going to write down B. But if we look at A is not changing. A just stays as 1 the entire time. So we're going to write down plus A. And that is our final output. So those of you who have been paying close attention will realize that this is just a super simple OR gate, which is exactly what this is right here. And the truth table for this OR gate is exactly the same as the truth table we got for the giant circuit over there. So hopefully this all made sense. If not, then do not worry, because next episode we're going to go over a lot more examples, and I will make sure that you know how to do this, because this is one of the most important skills you can have as a redstone engineer or as a real-life engineer. But yeah, that's about it. I hope you found it helpful, and I'll see you in the next one.